All right, good afternoon, everyone. It's my pleasure to introduce Mr. Gabe Kafity today. Mr. Kafity is a partner solutions architect and from Amazon Web Services. Um, uh, he's a specialist in data, AI, and high performance computing. He has a decade of experience working in the technology industry, holding a bachelor's degree in engineering from VirginiaTech and a master's degree in analytics from Georgia Tech. So without further ado, I'm happy to introduce Mr. Kafity.
Thank you very much. Thank you all for having me. One of the favorite parts of my job is engaging with emerging STEM leaders like yourselves. When I was a student, this was one of my favorite parts of my academic experience, is when people who were a couple of steps ahead of me and already in industry would come back and talk about their experiences, tech trends, things of that nature. So I appreciate everybody's time and attention here this evening, and I'm excited to speak with you all. So, yeah, as the intro said, Gabe Kafity. I work at AWS. I'm a solutions architect there. It's basically like technology consulting. I work with customers to get the most value out of AWS technology for their businesses. VTISC grad in 2019. Had a lot of good years in Blacksburg. Yeah, studied analytics at Georgia Tech part-time while I was working full-time. What else? Yeah, I've always kind of worked in the data and AI infrastructure space. So prior to AWS, I worked at a database startup for quite a few years. And then before that, I was at a data center storage company called NetApp. That was the first job I had out of undergrad. Yeah, so we'll go ahead and kick things off. Feel free to keep this as conversational as you'd like. If you have any questions throughout, raise your hand. We'll have some time at the end for Q&A as well. But this session is for your all's benefit. So please feel free to engage as much as you'd like to. So basically, the title of the talk is Career, Cloud, and AI. I would say the more accurate title would probably be like AI and then some like high-level career stuff. It's like not necessarily as much as heavy on the cloud piece or on the career piece. It's like kind of some AI fundamentals. So on that thread, I want to like pose a big question at the beginning of how much do you think the world can change in your lifetime? I don't know about you all, but things are moving very fast right now, and it's very exciting and it's very scary at the same time. Like, in my opinion, I think it's the most exciting time to be alive, to be working in technology, to be studying STEM topics. But the rate of change is kind of astronomical right now. So if we look back over the last few centuries, basically since the founding of the U.S., this is a analysis from ARC Institute. Basically, this is the estimated economic output based on emerging technologies of those time points in history. So you see some big ones on here that really affected the productivity and the output of civilization, like things like steam engine, railroads, electricity, internet, etc. And we're currently on the cusp of a explosion of the intersection of a few different of these technological waves. So if we do like, we have some technologists in here. So if we run a clustering algorithm on these different trends, it would basically go into 4 different buckets that we could label as these different industrial revolutions. So when the first industrial revolution was more so focused on things like textile mills, interchangeable parts, and water power machinery. Second one was mass production with Ford and the Model T and assembly lines, railroads. The third one was the big internet wave with computing becoming more baked into everyday lives. And then finally, we are on the cusp of the 4th industrial revolution with advances in technologies like robotics, energy, AI, cyber, quantum, you name it. all the things that you all are studying and researching. Like I went through earlier and saw one of the chip design labs here, and I mean it's honestly amazing, some of the work that you all are doing in research, and I'm very excited to see that all continue for you all and see how that can translate into your industry experience as well. So in an interview recently, like Bezos isn't super involved in Amazon anymore, and he hardly ever does interviews, but he did one a couple of months ago in Davos. And basically the key takeaway was we're currently at the epicenter of multiple simultaneous golden ages. So if we think about that bucket, that fourth industrial revolution bucket of things like AI, robotics, energy, et cetera, those are basically these different golden ages that we're talking about. So if we peel the onion on that a little bit more, like what is the common thread of those simultaneous golden ages is, if we abstract away all of the complexities, it's fundamentally the combination of three core resources that are continuing to improve in quality and in complexity and in strength, month over month, year over year, being data, algorithms, and computing power. And again, I'm sure this is no secret to everybody in this room. You all are, studying engineering at a world-class engineering organization, but this is like a large trend currently in industry where more dated types of companies that are not as forward-leaning, as technologically enabled, are really there's a bifurcation happening where companies who are being able to be more nimble and are able to adopt some of these technologies and address like the shifting ground underneath us are able to gain competitive advantages in whatever industry they're playing in. And then we see on the flip side, companies who are kind of having a lot of trouble with that, and it's leading to a lot of like turmoil for those organizations. So I thought this one was kind of funny. It's like a table full of screws, right? And you don't hammer a screw, use a screwdriver. So it's like, okay, we have this tool of AI that it's like, all right, we're supposed to use this thing for everything. So it's like, well, like this is kind of how it feels, right? It's like there's all this marketing out there about like AI everything. This is like going to change the world. It's going to be awesome for everybody. All of our jobs are cooked, like the whole 9 yards. I don't know. I just thought this one was funny, so I put it in here. But if we like kind of peel the onion on what it is AI actually is, it to help understand the current moment we're at, it helps to look backwards in history. So, like I know we talked a little bit about golden ages earlier, but now if we like look at AI specifically in the AI timeline, where there have been summers and winters in this field of artificial intelligence, machine learning, computer intelligence, whatever you want to call it, for basically the last 100 years. So this one stops with the ChatGPT moment, and obviously this could have been extrapolated out past that, and we would have seen like a bunch of other things in there, like one-shot learning, and then reasoning, and extension of context windows, and all the complexity past that. But like I want to go back to that crucible moment and kind of look backwards to the left. So what enabled ChatGPT to happen was the transformer architecture that was published by Google in 2017 in the paper Attention is All You Need. And that is the fundamental like algorithms and design principles which led to this wave of deep learning, which basically powers all of these large language models and like AI apps that we're using nowadays. Like the industry standard today is the transformer architecture, which was released in 2017. And then it basically sat on the shelf for a few years. Like Google had this innovator's dilemma where they had this huge business of like search and advertising. And they also had like the best AI researchers in the world. So this thing kind of sat on the shelf for a few years. And it took another like research startup, OpenAI, to pick up this technology and actually apply it and productize it to see the value of it. But then if we look even back further than that, in 2012, AlexNet was another crucible moment, which was the first time that any sort of these neural networks were running on GPUs. So this was like a super simple use case where they were doing image detection of cats. So it was, a very brute force, way to go about it beforehand, like with, all these different decision trees, super long computing times. They were able to migrate one of these models onto a GPU, and it wasn't one of these large server GPUs that people are running on today. It was like a local one, right, running just a few like GPU cores. And yeah, so 2012, first time that we're like, hey, AI runs really well on GPUs, which obviously led to like the explosion of NVIDIA since then. I don't want to like go through all of this, but basically like one of the super interesting parts is like all of these scientific enhancements are computing was just kind of the way that they were expressed. They're all reverse engineered from biology, like from a neuron in the human brain that has input with some activation function and then an output. So that's what we're going to talk about a little bit. So the whole concept of AI is basically this is like baking it down to its most simple form. It's a combination of all of these different artificial neurons, which are based on like a human neuron that like you'd have in your brain, right? So we're no strangers to like models, functions with inputs and a desired output. You all are probably taking courses where you're doing things like that today. So if we bake it down to this, like we have our inputs, our biases. Each of those have a weight associated with it, some sort of activation function, and boom, we have an output. It's like, hey, we have this input matrix, we do some computation on it, and we have an output. So that's a single artificial neuron. But where the actual like value realization happens in this type of paradigm is when we're able to stack multiple neurons together and then multiple layers of those neurons over and over. So again, basically, each one of these different inputs, we could just think about it's a matrix. It goes through different steps of different activation functions. Under the hood, this is all linear algebra. You get a data structure in, do some computation, pass to the next node. That output is another data structure, computation, pass to the next node, right? It's all just like complex layering of linear algebra at the end of the day. It's matrix multiplication. Okay, so if we look at an example, this is what like a computer vision example would be like. And this is a super simple one, right? So, okay, so our input is a picture of George Washington. So in this example, we have a few different layers where each layer is performing a different type of function. So layer number one, identify the light and dark pixels. Like, why is that beneficial? Because when we see where there's a sharp change from one pixel to the next, light and dark, that helps you identify an edge, which is the next layer. Okay, so now we're starting to identify like what the structure within the picture is. And then, identify combination of edges, each layer just getting a little bit more complex, building on the output of the previous layer. Then we're able to identify features. And then finally, we have our output. Hey, we think this is George Washington with 97% accuracy based on all of the computation that happened through this structure. Okay, so we're going to kind of look at how the sausage is made in the next one here. But like, I don't know, I've been talking for a few minutes. I'm going to take a sip of water. Like, any thoughts, any questions? Like, anything sound crazy? Anything sound cool? No? All right. Well, we'll keep going then. Okay, so this is the high level of like, all right, so we're going to create ChatGPT for the first time, right? And we're going to make this super, super simple. Okay, so step one, download the internet, right? Super, super easy task, right? It's like the whole internet, like, is the text on the internet, I should say, is like, there's not that much of it. It's like the text is a very effective way to store and transmit data, right? And if you do things like compaction and compression, like it's really not that much data. So there's a bunch of data cleaning on the front end. I'm sure everyone's done like some sort of data engineering work in their studies and their personal projects, et cetera. So let's assume we do all of this data engineering with things like URL filtering, text extraction, et cetera, et cetera. And now we have our nice clean input data set, which is all the text on the internet. And then the next big step is tokenization. So who's familiar with tokenization? Like is anyone like, yeah, show of hands. All right. So people have heard of tokenization. Basically, this is the process of translating English language into machine language. So like we talked about how AI is basically just vector processing and matrix multiplication. The inputs and the outputs of those AI systems are just these vectors. So like when you think about tokens, like a token is expressed as just like a vector is how we would think about it, or a matrix. So let's actually look at an example of what tokenization would look like. So this is an example, just like some simple web apps. So this is using GPT-4o. Every tokenizer for different systems is going to be a little bit different, right? Like these are all kind of built from the ground up, but the core fundamentals is the same. So like people ask like, what is a token? This kind of exemplifies that. So it's like, so I'll say, I am so honored to speak at VT Alexandria. So we can see like some people think, a token is a word, and like, yes, it can be, but that's not always the case. So we can see like I by itself, that's a single token. One space, AM, another token, right? So we get kind of a look here. So if we look at the word Alexandria, like white space, Alex, and Ria, 3 tokens for this embedding model that it generates, right? So like we put in some English, there's a tokenization algorithm, and then based on GPT-4o's tokenization algorithm, the vector output is just this matrix, this vector. Simple stuff, right? Okay. We talked about tokenization, neural network training. This could be, a 400 level 6-month course, right? So, I mean, just like keeping it extremely high level, we are creating the token prediction machine in the training step. We're using that clean data set that we had, and we are creating a probability machine to predict what is the most likely next token based on input tokens. So in this example, I'm viewing single, and then you have like a probability distribution of what the potential next word or combination of tokens would be. So 2% chance it's direction, 1% chance it's case, 4% chance it's post, et cetera, right? So in this example, hey, post is the highest probability, which is post is just like the English translation. The actual output is 3962 as that numerical representation. So basically, like these neural network internals are just a combination of all of these different activation functions. So let's actually look at what that is. Like we can look at it like this is a giant mathematical expression, but that doesn't really mean anything to me. I'm more of a visual learner, so I think that this is a helpful visual. So basically, like this is a system of a transformer architecture. So let's look at the left pane here first. So basically, we have this embedding step that we just discussed, translate natural language into machine understandable matrix. And then we have a bunch of like components within the transformer architecture itself, things like layer normalization, self-attention, feed forward, etc. And then it goes through this entire pipeline. Like when we talk about a transformer architecture, this is exactly what it is the combination of all of these different algorithmic steps passing pieces of data to and from each other. And then at the end, we get this output vector and translate that back into English. So if we look at the actual nodes themselves, so we talk about like parameter counts with these models, right? Like, has anyone heard that? Like, oh, I'm using like the Llama 3B, like it has 3 billion parameters, right? Or, you know, some of these are having like 100 billion parameters. So this is a visual representation of what those different parameters actually represent. So we can see like at every layer, like this is what the embedding step looks like. Again, just a bunch of matrix multiplication with like passing data across different activation functions. So if we just come look in, yeah, you know, it's linear algebra. It's vectors and matrices being multiplied together. Like there's, like, I guess my point here is like, it's a computing system that's kind of like a probability machine based on the things that it's trained on. In my opinion, this is not like some sort of, you know, conscious system. It's just like, it's a probability machine based on linear algebra. So we took a look at this example. So this is nano GPT, and we can really see like how the complexity goes exponential. So like if we look at, you know, GPT-3 compared to nano GPT, which was just up here, you go from, you know, a few thousand parameters to a few billion parameters. The complexity of the system kind of goes up exponentially at that point. All right. Cool. And then I think for this, at this point, if I play a video, will they be able to hear it? Okay, let's try that. So I really like this YouTube short. I think it kind of exemplifies these points well. It's like 30, 40 seconds, so I'm just going to play that quickly. My volume up. All right, so I might have to unmute my laptop, and then I might get some reverb from. Let's just try it. All right, get ready to plug your ears if this doesn't work.
Hitler plus Italy minus Germany. This came up in a full video that I did dissecting what happens inside large language models. You see, with tools like ChatGPT process text, the first thing to do is subdivide it into little pieces and associate each piece with a large vector, some long list of numbers. This is called an embedding of that piece of text. And it's helpful to imagine these embedding vectors as directions in some very high dimensional space, even if we struggle to concretely visualize anything more than 3 dimensions. Models that learn to embed words as vectors like this often encode a meaning into the directions of this high-dimensional space. If you take the difference between the embeddings of man and woman, and you add that to the embedding of uncle, you get a vector very close to the embedding of aunt. If you take the embedding of Italy minus Germany, and you add it to the embedding of Hitler, you get something very close to the embedding of Swedish. It's a good model to associate some directions in this high-dimensional space with Italianness and others with World War II Axis leaders. What is Hitler plus Italy?
So that's the general. Wow. That's the general idea. And in this example, it puts it in a 3-dimensional space because that's super easy for humans to visualize. Like the actual density of the like problem space is way more than 3 dimensions when it actually comes time to run these models. So like we do X, Y, Z axis, we visualize it, we kind of understand what's going on, but in reality, there's no way for us to like visualize the massive number of dimensions that these systems are computing. Okay. Let's see this one. Okay, so we had this 2012 AlexNet moment that we talked about, and like, yeah, this is Jensen from NVIDIA. So of course he's like talking about, hey, this is the first time things ran on a GPU, right? Because like now this is like his whole business. They're at the middle of this stuff. But basically, like we went from a perception AI, like this is the advanced analytics era, big data era, things like speech recognition, medical imaging, et cetera. We get into the wave of generative AI. So this is like, right around the Chat GPT moment. You could have, these AI bots do digital marketing for you, content creation, help you out with your studies, et cetera, whatever it is. We're kind of in this transition period. Like, has anyone heard of OpenClaw? So that's like it's the fastest growing open source library of all time, biggest open source library of all time, past like Kubernetes, past Linux. But that's like the gold standard for agentic AI right now, which is basically like you give like these systems having access to tooling and to other systems so that they can orchestrate, workloads for you, right? Like if they have access to your email, to your calendar, to like, some third-party services and tooling via MCP servers or something, they could send an email for you. They could book something for you, get your flight ticket, whatever it is. And then finally, like the one that's like not quite here yet. Actually, I was just in San Jose last week and I took a Waymo for the first time, and that was awesome. Has anyone been in a autonomous car before? No, not yet. I would recommend it. I thought it was so cool. I sent a video in the family group chat, and my mother-in-law said, "Get out of that thing right now. I'll kill you if you get out of that." So I thought it was awesome. It felt like it's one of those where it's like the future is already here, but it's not evenly distributed kind of feelings. So that's kind of where we are with like physical AI, things like self-driving car, general robotics. When I was in undergrad, in Blacksburg, there's a Volvo manufacturing plant like 30 minutes from Blacksburg. I did a co-op there in the paints department when I was in school. Great place to work. I learned a lot. But so in the paints department, I was like doing time trials of the robotic arm going and doing like quality control of how precise the movements were. Anytime we wanted to tweak how the robotic arm was moving when it was painting this truck or whatever, it was like manual tuning of some hard-coded script of how this thing would move. There was like zero automation at all. If you wanted the thing to move 1 second later or 4 degrees more, you would have to like take that measurement and then figure out how you have to change your script in order to make that thing move differently. Like a lot of these types of functionalities are currently in the process of like being automated with some of these deep learning algorithms that we're discussing. Let's see. Just a fun one. Met Jensen at GTC DC last year with some of the AWS team. His security detail was not pictured here, but it was very large, as you might imagine. Cool. So we kind of touched on this piece a little bit. Again, I don't think these are conscious systems. I think they're probability machines that can help us achieve things. Humans solve problems end to end. AI solves problems middle to middle. So it's like humans set direction, decide what is purposeful to do, and then outsources tasks to AI is kind of how I look at it. So the evolution of that goes from we use these types of big data systems for analysis, like, okay, we want to do some sort of forecasting based on historical data. We get into the chat era. Okay, you can ask some questions, which is like a more improved version of search. We talked about like agentic models and taking actions. Hey, I just like speaking to my phone. Hey, check availability for the 3 people on my team for next Tuesday, and then book a meeting based on everybody's availability. And then finally, like automation, which is the combination of actions and the physical world, which Waymo is a cool example of. I thought that was really fun. Yes. Question in the chat. Let's hear it.
Okay. There's actually 2 questions.
Okay.
Okay. Do the magnitudes of the token values mean anything? Are more complex models better at these embeddings?
Do the magnitudes of the token values mean anything? A lot of it depends on the embedding algorithm used. And this is like part of why AI gets the rap of like being a black box is like we translate English into these vector embeddings, and then we have like these systems that are processing the vector embeddings, and we can lay out the logical flow of these systems. But with regards to like how they're actually being processed, like it's kind of hard to understand what's exactly happening in that system. Is kind of my first thought. But do the magnitudes of the token embeddings mean anything? I would say, like, yeah, different models have different sizes. They'll output different vectors based on those sizes. So, like, different things are, like, there are models that could run on your phone, and then there are models that you need, like, you know, a server the size of this table to run on based on the size of it. So each one of those would kind of have, like, different characteristics with regards to the first question. Okay, and then the second one?
Is an open source model like OpenClaw better than subscription-based models such as ChatGPT Plus or Claude Pro?
So using the word better is tough. Like there are these benchmarks, but then a lot of models game the benchmarks. It would basically be like, you know, oh, we want the model to be really good at the SAT. So we gave it every single SAT that was ever taken, and surprise, it scored a perfect score, right? Like, so there's, you can kind of game the systems. There was a, kind of early on, there was a idea that models would be like super general and it would be winner take all, one model to rule them all. And it's actually, we're seeing more of like a divergence of specialized models for certain types of use cases, for things like coding, for things like legal advice, for things like medical advice. So, and then with regards to open source versus closed source, this is a debate much older than AI. This has been like since the beginning of like enterprise computing. Like this is the Linux versus Windows debate. This is the iPhone versus Android debate. It's all kind of the same, and I think it's good for both to exist because it creates competitive pressure, which ends up being good for the consumer. But with regards to like, is Claude better than DeepSeek? Like at some things for sure, but like if you just want to have something for free running on your laptop that can do like 85, 90% of the things you want it to do, like it's a trade-off there. It's not like one size fits all, one is always better than the other. All right. So the unsexy part nobody wants to talk about is how much data engineering is required on the front end of these systems. It is like not all AI research. It is a lot of large data processing, data cleaning. So like we don't like, yeah. So it's basically like this infinite loop of data engineering on the top. Like I'm not going to read every single one of these tiles, but then it's like we get into the AI model training piece. Like, does everyone kind of understand the difference between training and inference? Like, so training, like super simple. Training is creating models. Inference is using models, right? So we do all of this data engineering. We train a model, which means like we're creating a technical asset. We're creating a piece of software that is a model. We can then do model evaluation with all of these benchmarks that we're talking about. We could do things like reinforcement learning where, hey, we're going to show this to some users, and based on the output, they're going to give us thumbs up or thumbs down. And then based on that feedback, we can use that to further enhance the model, things of that nature, do a bunch of systems validation, et cetera. And this loop just kind of goes and goes and goes. Yeah, so it's a lot more than just AI researchers. There's like an entire ecosystem of engineers that are required, and scientists, and like a bunch of different like folks to kind of keep this whole life cycle running. So this is kind of where like enterprise computing is going, or just like computing in general. Like I come from the enterprise space, so that's my bias, but we'll talk a little bit later about enterprise versus consumer. Yeah, so we have these two rectangles. The top one is creation. We have infrastructure as inputs. This is land, this is power, this is chips, this is, you know, all the things that we need to kind of like create a data center, for lack of a better term. Output is models, like super simple. Like, how can we make this as simple of a system as possible? We then have that technical asset to run inference, which is usage of these systems. So then applications are often creating tokens via embeddings, like we discussed. These tokens go through that whole, you know, multi layer perceptron model that we were looking at earlier. And then on the other end, like, you know, it goes back and serves that application. But there's this trend now called like tokenomics, which is what a lot of these companies are kind of optimizing for, where it's like, basically these are just becoming like manufacturing plants, but the output is digital, not physical. It's tokens. So then companies are thinking about, when they're making investment, like, how can I optimize as much as possible for tokens per dollar per watt? And it's extremely expensive, right? So like, you see the capital expenditure of the hyperscalers, right? And this doesn't even include 2026, which, like, this is an old graph. So it's like, in this one, like, Amazon was 97 billion estimated in 2025. I don't know what it actually ended up being in 2025, but committed to 200 billion in CapEx for 2026, largely going to like AI infrastructure, AI data centers, and the same with the rest of kind of like these hyperscale companies, like really doubling down on their investments here. And then also we can look at some projected trends of electricity consumption based on, not solely based on the expansion of these like AI factories, but that's a large part of it. Why is all of this investment happening? Because of scaling laws. So we talked about compute, data, and algorithms. As each of those three pillars is continuing to improve, we're not hitting a point of diminishing returns with how good these things are getting. It's like, you know, the capabilities of the models that are being created are, you know, doubling every 6 months, you know, roughly, right? And I'm sure we all feel it in the usage of these tools and how fast it feels like things are moving. But yeah, like these scaling laws are continuing to hold as compute algorithms and data are all getting more complex, improving in their quality. We're able to just make these systems bigger and bigger, and that is making the outputs better and better for all of these models, whether it's like, you know, GPT from OpenAI, whether it's Claude from Anthropic. Those are like head and shoulders the leaders, but you know, you got Meta with Llama, pretty good. You have a bunch of like solid open source Chinese models with like DeepSeek and Kimi and Qwen. Yeah, all of them are kind of reaping these benefits of the scaling laws. Has anyone heard of Jevons paradox? So, okay, so this one is actually not a technology concept. This is a economics concept. When simply put, it's making a resource more efficiently leads to an overall increase in its consumption. So if something's produced more effectively, more people want it. So there was this economist in Great Britain in the 1700s, Stanley Jevons. His theory was that the steam-powered engine would actually lead to an overall increase in coal usage, which it did, based on the unlock of additional use cases and additional industries. So the steam engine made the cost to produce and use coal way lower, and then the consumption of coal went way up. We're seeing something similar now with AI when it comes to token production cost and consumption. So if we look at this graph, the blue line that's going down, cost to produce 1 million tokens. The red line skyrocketing is token consumption, right? So as it continues to become more cost effective to produce tokens, the theory is it will lead to an overall increase in the demand for those tokens. And I don't know about you all, but I certainly, in my personal life, in my professional life, I feel that theory staying true with how much people are depending on these tools and integrating them more into their daily workflows. Okay, so the talk was called Career, Cloud, and AI. We're done with the AI stuff. So now we're going to talk about like some tech industry stuff, some career advice. Again, if we have any questions at all throughout, like please, speak up, let me know. Let's see. We're at 4:42. Okay, so I'll get us out of here on time. Don't worry, and I'll leave some time for Q&A. So, what is the composition of a company? Like, why do companies exist? Typically, like to pursue whatever sort of mission that they are set out to pursue, right? So for nonprofits, that could be like improving the world in a particular way, whether it's like, food insecurity, shelter, whatever it may be. But for most people, they end up working at organizations who are like for-profit entities, where you want to create something that is valuable, that people will give you money for, such that you make a profit on top of that thing that you sold them. Like super simple stuff, right? I'm not telling you all anything you don't know. So step one, create a product or service. So this could be like, software, hardware, services, consulting, whatever it may be. A big piece people don't think about is distribution. So like as technical people, I feel like we often think about the product, like build it and they will come. This thing is going to be so freaking awesome that everybody will use it, period. And that is not the case. Like, if people don't know about what you're offering, they have no opportunity to consume that product or service, which is where distribution comes in. Things like marketing, sales, delivery, customer service, and support. Like, what is the customer life cycle for the business? Everything from them understanding what the product is, what the company is, to going through some sort of trial period, deciding they'd like to move forward, purchasing that solution, implementing that solution, having success with that, being supported, deciding they want to continue to use it year over year, et cetera. And then there are like supporting functions within organizations, obviously, finance, accounting, IT, HR, legal, et cetera. Yeah, so that's a big one. I mean, like show of hands, like who, like have people had internships at for-profit organizations so far? Okay, about half the room or so. Has anyone worked at a nonprofit? Nobody in the room. Maybe somebody on the phone, just out of curiosity. Okay. Cool. So with regards to the technology industry, these organizations typically fall into two buckets, consumer and enterprise. I've worked predominantly within enterprise in my career, but people make great careers in consumer as well. Often consumer companies are the companies that, like, if you tell your family you work there, they're like, everyone knows what it is. And enterprise is like, I don't really know that company. I don't really know what they do. But regardless, I digress there. So like example, like what is the difference? A consumer company creates products and services that individuals use. So think about like, you go to ChatGPT on your iPhone, you're using two consumer products right there. Then you swipe over, you're on TikTok, there's another consumer product. You go and get in your Tesla and you drive to go do an Amazon.com return. Okay, so you're just like engaging with a lot of consumer products at that point in time. What are some enterprise companies? These are companies whose main customers are other businesses. So like B2B type of companies. Predominantly here, you'd have like Anthropic. Like, yeah, people use them from the consumer side, but the bulk of their customers, their revenue comes from other companies. And then like a lot of big tech companies are enterprise companies, Microsoft, NVIDIA, Databricks, AWS, et cetera. So what are the goals? Individual engagement versus like business outcomes. So typically consumer products are like we need to be viral, we need to spread like wildfire, or we're dead. Whereas like the reason enterprise companies is like, all right, we need to either make our customers more money, save them time, decrease their risk, like one of those different types of things. How do they make money? Typically, consumer is one of two ways. Either they do advertising, meaning you get a bunch of ads, like you're on YouTube and you see the ads, or you pay for YouTube Premium or subscription, whatever they call it. You get the ads removed because you're paying for the service as a subscription. Whereas enterprise companies do like long-term contracts for licensing. It's like, hey, Anthropic, I run an engineering department with Y number of engineers, and we're going to give you, $1 million a year for the next 5 years to use Claude for our engineering team. Yeah, some trends here. All right, I feel like I'm just reading off a slide, so I'm going to be done with this one. Okay, so this one's like just some career advice. I don't know, like this, I have like 6 bullets here, and I could have, these are kind of in flux, so we'll see. Okay, so career growth is effort times opportunity. Notice how it's not effort plus opportunity, because both of these really matter a lot. And yeah, like there was a saying that I liked a lot that was like, if the hardest working people if hard work is all that mattered, the most successful people would be, the people who manage like a 7-Eleven, or like, do some sort of manual labor job that is long hours, that is often backbreaking. Opportunity identification is the high leverage point in this equation. Effort has to kind of be a given. It's like that one is, if you want to be competitive in any field that you're doing, you have to like put effort forward. But opportunity identification is really the high leverage task where you can have the highest potential expected value based on that opportunity that you select. Okay, speed versus quality. So Amazon has a concept known as one-way door and two-way door decisions, where a two-way door decision is something that should be done very fast. The concept is it's a two-way door. You can make the decision, and if the decision doesn't go well and you want to pivot, no big deal. You go right back through. So you can exit the door, you can re-enter, no big deal. And that is 90% of decisions that people have to make in school, in work, in life. Don't put such a cognitive load on yourself with these types of decisions. Make them quickly and adjust as needed. Where quality really matters is these one-way door decisions, which is the minority of decisions that people are going to make. These are like 5 to 10% of your decisions, where you're thinking about, what job do I want to take? What city do I want to live in? What school do I want to go to? Things that are like have more long-term effect on your life. Those are the things where you really want to actually sit and be thoughtful, contemplate, and have a higher quality decision bar. But again, like the emphasis here is 95% of decisions you make in your day-to-day life, speed should be what you're optimizing for, and you can always pivot as you go. Okay, grit, and curiosity, and intelligence are listed in a very purposeful order, because they are listed in an order of what you have the most control over to what you have the least control over. So grit is basically just like effort, hustle, caring about what you do, having a little bit of passion. That is something that anybody can do, and it's a skill. Like the more you do it, the more you will have the ability to continue to do that and to persevere. Being curious is something that, again, people have a lot of control over, right? You can, like I listen to like tech podcasts in my free time. That's just what I think is fun, because I'm curious and I'm passionate about the topic. And then finally, intelligence is listed last, because like, you can study, and you can learn new things. Everyone can learn new things and is highly capable, especially if we're here. This is a highly competent room, but at the end of the day, like, you can't really change your raw horsepower that much. Okay, so you can do anything, but not everything, meaning focus is super important, okay? So this one pairs nicely with speed versus quality, in my opinion. So, like, yeah, you can do anything, but not everything. Focus is super important. I'll leave it at that. Networking, and like, this isn't like the corny version of like, go to the thing and put on a fake face and meet the people. This is like, humans are a very social species, right? And like the people that you surround yourself with matter a lot. So it's like you're currently choosing to attend this talk on an evening weekday, right? So like you're choosing to be in a network of curious individuals who are like interested in a type of talk like this. You are in this program, like a prestigious master's program next to a big city. That's another like type of network you're putting yourself in. Who you like hang out with outside of school and work, that's another network. So like just be conscious about who you're spending time around, because like the corny saying of like you're the average of the 5 people you spend the most time with is certainly true in my experience. And then finally, simplicity is everything. We're engineers, we're technologists. We make everything way too complex, and it frustrates most people. Like, fight for simplicity, make things as dumb simple as possible. That's why Apple is so successful, and everybody in here has like multiple of their devices like sitting right in front of them because they focus on simplicity. Okay, so your call to action, be gritty, be curious, own your career, have a high bias for action. Yeah, do what you like to do. There's some links here that I thought might be helpful. Like if you're interested in cloud stuff, AWS has a bunch of free training resources, a bunch of like jobs posting. It's that time of year for new grad jobs, internships. So take a look. Add me on LinkedIn if you want. I have some book recommendations here. But that concludes my talk. So with whatever time we have left, I'd love to like take questions if anybody has any.
Any questions?
Yeah, sure. I'll ask one. Thank you, Gabe. Yeah, super insightful. I had a question. I think this applies to a lot of us, junior technical people who, I think a lot of us are, if they wanted to step into a solutions architect role, such as yourself, what is the best possible way to do that?
So I have if you can please, Gabe, talk to us about your job, title and what it entails, and just talk to us about your job a little bit, please.
Yeah, absolutely. Okay, so it's a 2-part question. Like, talk about a solutions architect a little bit, and then how can people get into it? Okay, so solutions architect is a customer-facing technologist, and both of those parts are extremely important: the customer-facing part and the technologist part. You are responsible for working with customers to like identify pain points in what they're currently doing, bottlenecks that are going on in their current engineering systems, in their software development pipelines, in their AI application deployments, in their data lake architectures, and all of these different types of technical assets that these types of enterprises have. You're going in as a technical advisor to help diagnose problems and work with them on action plans about how to remove those problems, remove those bottlenecks, help them optimize systems. So sometimes it's net new system, and we're talking about strategy for building something from the ground up. Sometimes it's, hey, we have this huge data center and it's getting retired and we need to migrate, a petabyte of data and 1,500 servers to the cloud. And how can we do that in a phased approach? So that's kind of like the high level of the solutions architecture piece. It is a job where technical skills are required, but you are not coding day in and day out. You're doing some software development with the creation of things like prototypes and demos and like helping a customer with a specific configuration, but you're not building, operating, and maintaining applications. You do not touch production systems. The communication piece is very important. You will be communicating regularly with customers. You're going to have like emails in and out, like coordinating meetings, traveling to go see customers, that kind of stuff. How does one get into solutions architecture? Is typically some sort of technical background. So it could be like I started in software development, and then I went into IT operations, and then I went into like professional services, which is more like technology consulting, and then ended up in solutions architecture. So I had the technical chops from internships that I had during undergrad, and then the first customer-facing technologist role I had was like this technology consulting kind of role, and then went from that into a solutions architect type of role, which is more like a technical advisor. And just to be candid, like solutions architects, like some companies call them sales engineers, like you are working directly with salespeople at the company who you work with typically. And that's not everybody's cup of tea. That's how I got into it. And you gotta be kind of a self-starter. Like it's a kind of a notoriously hard field to break into, but it's like the most valuable skill sets are some degree of technical chops and then like very good communication and professional skills.
Thank you. Any other question?
And thank you to Pranay for teeing up this talk today. I met him at some of the VT master students came to Amazon HQ2 a month ago, and we met and got talking, and he's the one who created the connection for this talk today. So thank you.
No problem. Thank you.
Talk about important.
Okay. So this is regards to certification, which you have on the slide right now. Are there any certifications you would recommend for ISE students interested in AI or 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 their intersection?
Any certifications for AI? So this one definitely depends on the level of technical experience that you have. So like this is pretty true across industry certifications in technology in general, and it's true at AWS. So there are like 3 brackets of certifications. There are foundational certifications, associate certifications, and professional certifications. And it's what it sounds like, right? The foundational are easier, no experience required, not as much prep time required. You could get by with just like some flashcards, get some concepts in your brain, you're good to go. Associate, a little bit more prep, a little bit more hands-on experience, and then professional. With regards to the AI one, though, I would recommend if you're a like starter, I would say get the AWS AI practitioner. That is a foundation level certification, which you could pass that with taking like some 10-hour course online and just get like some core concepts in your brain, and you'll be good to go.
I have a comment, and I don't know if you want to elaborate. So I like what you said, humans solve end to end, whereas AI solves middle to middle. I like that saying. Can you just a little bit elaborate on that, please?
Yeah, absolutely. So, and again, like in a lot of my talks nowadays, I'm like repurposing things that like Jensen from NVIDIA has said. So this is another one from him is like the AI, like, okay, so what is it? It's a discrepancy between purpose and activities. So it's like a job's purpose. Radiology is the example. So everyone thought like, okay, with AI, radiologists are going to be completely replaced because AI can do a much higher fidelity job at a much faster rate. And really what has happened since the advent of AI is the amount of radiologists in the world and in the West has actually gone up, because the purpose of a radiologist is not to scan images. The purpose of a radiologist is to consult with patients, help diagnose their conditions, and help them get better. So although the task of scanning images was outsourced to an AI system that is much higher efficiency, the purpose of the doctor, of the radiologist, was actually enhanced by this system. So the purpose is the end-to-end customer wellness, patient wellness life cycle. I'm still in like work mode. The patient wellness life cycle, but the AI itself, you know, is just some convolutional neural network running on some server somewhere that can analyze, you know, 1,500 images a minute, which is like, obviously no human can do that. You need a lot of coffee to do that.
I think we reached to the end of time. So thank you very much, Gabe. This has been really an inspiring talk. Thank you.
Thank you all.